Bismillahirrahmanirrahim. BS Physics, Semester 1, Mechanics, Course Code Physics 1103. Dear students, Chapter number 6, Lecture 2. The name of lecture is Motion in the Presence of Resistive Forces. Dear students, I am talking with you, Rashmat Ali, Assistant Professor of Physics, Khaja Fareed Government Postgraduate College, Ramia Khan. The material of this lecture has been taken from the books as recommended by the syllabus outlines of BS Physics Mechanics. The first book is Physics for Scientists and Engineers by Sir Javed. The second book is Fundamentals of Physics by Halliday and Resnick and the Charles Walker. Dear students, the title page of this chapter with a diagram of merry-go-round is shown in here. This lecture has the main contents: motion in the presence of resistive forces proportional to the object's speed, terminal velocity, air drag at high speed. So, dear student, we are seeing the first topic, as this lecture is very important in both respects: objective, subjective, as well as short questions. The first part of this lecture is the motion in the presence of resistive forces. First of all, resistive is a word taken from the resistance: to resist, to oppose, to stop a moving body. The resistance forms a force that stops a moving body. So, motion of a body when resistive forces are present. First of all, we study about the resistive force, the typical definition, that is, when a body is moved through some fluid, liquid or gas, an opposing force to the motion of body in a fluid is called resistive force. Here, fluid, anything that has ability to flow. So liquids can flow, gases can flow. These are the fluids. As fluid is a medium, when any body is put into the medium or fluid, it moves through it. Due to medium, some resistive force acts on upon it and tries to stop its motion. Resistive force is a force and its force is a vector, so it is denoted by R, a bold-faced letter of resistive force. The air resistance associated with the moving vehicles. This resistance can also be named as air drag. And the viscous drag, viscous forces acting on the bodies moving through liquid are the two examples of resistive forces. So we can see a sphere or ball in red color is put in fluid like water. When it put it into the fluid, it starts moving down due to its weight mg. And due to velocity v, the resistive force acts in upward direction. The magnitude of R depends upon the speed of body, and the direction of R is always opposite to the direction of motion of body, as we have seen from this. R is in opposite direction to the V. R depends upon the speed in a complex way. The first case is that the resistive force is proportional to the speed of moving body. Where happens this? This is the case for those bodies which have small, very small speed and very small size, whereas small mass, small weight. As we have seen, the sphere is moving through the fluid in a container, in a beaker. So, particle moving through air, R is proportional to V, so R is equal to minus B into V. Negative sign indicates the direction of motion is opposite to the direction of velocity. And B is a constant. We discuss it in detail in the further coming article. The second case, the resistive force is proportional to the square of the speed of the moving body. Where happens this? This case is possible for large bodies and moving with high speed, such as skydiver moving through the air in free fall. We can see in the figure a paratrooper or any other body. We see the relation in which 1 by 2 dA rho into V square. 1 by 2 dA rho are the constants and V is the velocity, that is a variable. So, we know about the resistive force proportional to the object speed. The first case, when a body is a very small size, small mass, small weight and moving with a small speed as particle moving through the air. So, R is proportional to V and R is equal to minus B into V, where V is the velocity and B is the constant whose value depends upon properties of medium, the shape, and the dimensions of the body. Properties of medium means nature of fluid, whether it is air, water, or any other fluid. And shape means whether it is in a rod shape, sheet shape, plane shape, cube shape or sphere shape. And the dimension means its size, that is length, breadth, height in case of cube or any other cuboid, rod or plane sheet, and the radius. If the body is a sphere of radius r, then therefore b is proportional to the speed r, radius r, b is proportional to r. The negative sign indicates that r is in opposite direction to velocity v. So we would like to find the relation for the velocity when a body is moving through the fluid. For this purpose, consider a small sphere of mass m, radius r, and released from rest in a liquid as in figure 1. We can see from the figure, and we can see the balls, spheres, when it is just released, its velocity is 0 and a is equal to g, that is the acceleration is maximum. We can see the arrows, 2 arrows directed downward. The length of arrow shows the magnitude. The right side arrow shows the acceleration or the force acting, net force acting, and the left side arrow shows the speed, velocity of the body in the fluid. We see that as the body moves down, the right arrow is decreasing, whereas left arrow is increasing. As the velocity increases, the acceleration of the body decreases. So, let the only forces acting on the sphere is the resistive force R equal to minus B into V acting down against the direction of motion, and the gravitational force Fg, that we can call it buoyant force, that is the weight of the body. Buoyancy is a process and buoyant force is a force that acts on the body when it is put into some fluid. This force is equal to the weight of fluid displaced by the body when a body is immersed into the liquid. So buoyant force is basically weight acting in the downward direction. Since there are two forces applying here, so Newton's second law can be applied to get the vertical downward directed motion. Choosing the downward directed direction to be the positive, we know the initial velocity, whether it is in any direction, is always positive. Then any quantity in the direction of velocity is positive, and in the opposite direction of velocity will be taken as negative. So here velocity is downward, so its direction is considered as positive. Net force acting on the sphere is equal to sigma y, Fy equal to Fg plus R. By Newton's second law, Fy would be equal to ma. Y is put here due to vertical or y component. Fg equal to mg and r equal to minus b into v. So, as we know, acceleration a is equal to dv over dt is in downward direction. So we can find the relation for acceleration in terms of velocity. dv over dt equal to g, taking the mass m in the above equation towards the right, it will divide the whole equation. So after division and simplification, we will get the acceleration in terms of velocity. dv over dt equal to g in minus b over m into v. This is a differential equation. It can be solved for velocity of the falling sphere at any instant. It means that velocity is going to change. As at the highest point velocity is 0, as it moves downward the velocity is increasing, but at some instant it becomes constant. When acceleration becomes 0, velocity becomes constant, and this velocity would be called as a terminal velocity. So we say when v equal to 0, putting the above equation, the magnitude of resistive force is 0 and the acceleration dv over dt would be equal to g. As time increases, the magnitude of resistive force increases and the magnitude of resistive force approaches the weight of the sphere. In this situation, the speed approaches to terminal velocity. V is the velocity and T is the terminal, written as subscription. We can see here the terminal velocity is written by Vt. The relation is continued as the slide is going to change. Now integrating the above equation on both sides by using boundary conditions. Here boundary condition will be when time is 0, then velocity is also 0. As the time passes to t, then velocity becomes v. So integrating the above equation and managing, separating the variables, so we have this relation. Now we see the integral of derivative of some quantity divided by some quantity would result into logarithm. Simplifying this equation, we have this relation, and integrating the time as it is only the single factor, so we get the upper limit over lower limit by only t. Taking the constant from the left side, m over b, to the right side, so we get the equation minus b over m into t. And integrating the formula above, as minus b is the constant of v, multiply coefficient of v, so we arrange it for minus b, taking the limits, upper limit minus lower limit over the lower limit, we have b over minus b over m into t. The upper limit, replace v by v, the relation will be the same, and the lower limit, replace v by 0, the log will be log mg. So the difference of logarithm would be converted into ratio, division of the same quantities. Now taking the antilog, if we take the antilog, then we get mg minus b into v equal to mg is managed exponential minus g over m into t. And the velocity mg over b into 1 minus e exponential raised to power minus b over m into t. This equation of velocity when a body is falling through a liquid. Here E is exponential, E is the Euler's number. The symbol E represents the base of natural number called the Euler's number. And our Euler's number is always represented by lowercase e with the value 2.71828. This is a constant we must remember, keep in mind. Constant should be memorized. So for terminal velocity basically term at the end of a term the velocity of a body. As we have seen that the term starts when velocity is increasing. At some stage the velocity becomes constant. Where the body has velocity, constant velocity starts, the terminal velocity is present there. So we define the term velocity of a body falling through a fluid when the resistive force becomes equal to the weight of the body of the fluid, or the acceleration of the body becomes zero, is called terminal velocity. In other words, R equal to W, B into Vt equal to mg, and Vt would be equal to m over g into m over b into g. We also see some cases here when t is small. We also need the exponential series, that is the e raised to power x equal to 1 plus x square over 2 factorial plus x cube over 3 factorial and so on. When we put the value of x and replacing x by bt over m in the equation as we have evaluated it in the equation, then we can see that v equal to mg over b into 1 minus bt over m. So simplifying it, v would be equal to mg over b. In other words, v equal to gt. Case 2, when t is very large, that is approaches to infinite, and exponential infinite would be equal to 0. Again, putting this condition in this equation, we find some possible solution. So large speed, v equal to mg over v into 1 minus 0 over mg over v. Time constant. Time at which the release body droplet from rest reaches to 63.2% of the terminal velocity is called time constant. Time constant, since it is a constant m over v, it is represented by tau. So the above relation can be written in the form of mg over b can be written as terminal velocity, and tau for that velocity we would have the relation v equal to vt into 1 minus exponential minus t over tau. The velocity versus time, the graphical representation is shown here. Time is taken along x-axis and velocity is taken along y-axis. We see the exponential curve. As indicated in the graph, the lower portion, time for which the velocity of sphere of body in a fluid reaches to 0.632 times the terminal velocity is a time constant. Then velocity with time becomes almost constant. The line becomes horizontal. This is terminal velocity. The other article, air drag at high speed. When a body is moving with very high speed and having a very large mass as compared to the droplet, raindrop, then the resistive force would not simply proportional to V, rather it is approximately proportional to the square of the speed. The example of this resistive force can be observed in airplanes, sky drivers, sky cars, baseball, etc. The magnitude of resistive force can be expressed as R equal to 1 by 2 dA rho V square, where 1 by 2 dA rho, all are the constant, only velocity is variable. Rho is the density of air of medium. A is the area of cross section of moving body measured in a plane perpendicular to the velocity, and D is the dimensionless empirical quantity called the drag coefficient. D is 0.5 only, having no units. For spherical body as a ball, and capital is D is approximately 2 for irregular shaped bodies. Now, we find the relation for the terminal velocity. Since heavy body in form as sphere is falling down with velocity v due to weight mg and drag force, resistive force is acting in upward direction. At some stage, the velocity of sphere becomes terminal velocity or constant velocity. Consider the motion of a body in free fall. Resistive force acting on it is given by, suppose that the body has been released from rest as in figure. The forces acting on it are the downward gravitational force Fg equal to mg and the upward resistive force R. The net force is given by sigma Fy equal to Fg minus R, where putting the values sigma Fy equal to mg minus 1 by 2 into d a rho v square. So managing for the acceleration as shown in the red color equation, this is the acceleration of the body. Terminal velocity for a high speed. When acceleration becomes zero, then the velocity of body becomes constant. That constant velocity will be called a terminal velocity. From the above equation, if we put the a equal to 0, then we get g minus d rho a over 2m into v square equal to 0. So we can summarize the velocity as vt equal to square root 2mg over d rho a. Here a is directly proportional to r square. A is the area of cross section. Area depends upon the size of sphere, that is radius of sphere, as we know that the spherical area is 4 pi r square and some other bodies have different area formula. We have seen here mass is directly proportional to r cube. Because mass of body is a constant, density we defined here, that is mass per unit volume, and the volume contains r cube. So we can say that mass is directly proportional to r cube. From this relation, we can observe that all the parameters other than r are constant, so we can say that Vt is proportional to r square root. Some objects and their corresponding terminal velocity, we take two objects as an example. First one is the sky driver having mass 75 kg, cross-sectional area 0.70, then the terminal velocity becomes 60 meters per second. Similarly, the final example, we see that the end drop that is very small in size, 0.20 centimeter, the value of mass is 3.6. 3.4 multiplied 10 raised minus 5, and cross-sectional area, also the velocity becomes 9.0. Dear students, the lecture comes to end. I am very thankful for listening and focusing with patience. Allah bless you all.